We now consider how we can use our critical point analysis to work on application problems that involve optimization. So let's start off with the classic type of model. We've got a closed rectangular box. All right, we've got a box. There we go. Three-dimensional shape. It has lengths, widths, and heights. Let's call them X, Y, and Z because that's easier to read than L, H, and W's. We want a box to have a volume of 100 centimeters cubed. So the volume is 100 and the volume is X times Y times Z for a rectangular box. How can we build this box such that we obtain the minimum surface area? Well, let's take a look at how that would break down. So we want the surface area to be minimized. So we need a function for that. And the first thing we note is that this is a function of X, Y, and Z. Let's start off with that version. The surface area just for this box would be X times Z. And there would be two sides of that, two of those. There's going to be a Y and Z side and another Y and Z side, two of those. And last but not least, of course, we have the bottom and the top, XY and XY. Now, how do we implement this constraint? We're going to see a very interesting way to do that in the next week, or the next unit. But for now, let's settle for the classic method of using our constraint to eliminate a variable. And let's eliminate Z. So if we have V is equal to 100 equals X, Y, Z, then Z must equal 100 over X times Y. So our surface area as a function of X and Y together, and note no Z, or Z is gone now, our surface area would be 2X times 100 over XY plus 2YZ, but Z is 100 over XY, and we have 2XY as our last term. So this is the function of two variables that we're trying to optimize. So we're going to try to optimize S of XY. So we have our function, which is the surface area, and we're trying to minimize that. We've already forced the volume to be 100 by using our Z value as 100 over whatever we select for X and Y. Now, of course, we can simplify this right off the bat. We can cancel some X's and Y's. So let's do that immediately. And 200 over X plus 2XY. So our first step, if we're trying to do an optimization, and we recognize that there's some trade-off here. There's no simple answer. It's always good to look at the function and ask, well, what happens here? Well, as X gets bigger, this term gets smaller, but as X gets bigger, this term gets bigger, so there's a trade-off. We expect that there's going to be some sweet spot, some magic value of X that's going to minimize all of this. And likewise for the Y, because it's symmetrical that way. So our first thing is to search for the critical points, and for that we need our two derivatives. Our X derivative would be minus 200 over X squared, remembering that this is 200 times X to the negative 1. Bring the negative 1 down front, we get X to the negative 2, or 1 over X squared, and 2Y here. Our Y derivative will be the same, only with Y's, and plus 2X when we differentiate the last term, and we're looking for critical points, so we set them equal to 0, set our both partial derivatives equal to 0. And see if we can tidy that up a little bit. And I think the best we can do here is bring the 200 over, so we'd have, let's write it that way, 2y equals 200 positive over x squared. We can cancel our 2's and get 100. Likewise, we'd have, let's just go, we'll do it that way. 200 over y squared. Again, cancel the 2's, get 100 on the right. And now we have an equation here, an equation here. We're just going to put the first, which gives us a y in relation to x, so it lets us get rid of the y's in the second equation. 1 into 2 will give us x equals 100 over y 100 over x squared all squared. Better way to write that is 100 times invert this, x squared over 100 all squared. And we get 100 divided by 100 squared, that's 1 over 1 100ths, and we get x to the fourth. X to the fourth. So what does that tidy down to? That gives us x equals x to the 4 over 100. And let's do that over here. X minus x to the 4 over 100 equals 0. That's handy because it makes it possible to factor x, and 1 minus x cubed over 100 equals 0. And we keep solving, we keep solving. Let's go back this way. This tells us that either x equals 0 or 1 minus x cubed over 100 equals 0. What does that translate to? We would bring the 100 over. That's the same thing as x cubed equals 100, or x equals the cube root of 100. Double check that. Yeah. If x is equal to the cube root of 100, we'd have the cube and the cube root cancel. We get 100 over 100. 1 minus 1 is, in fact, 0. So last but not least, if we have x equals 0 and we put that back into 1, if x equals 0 means y is going to be undefined. That's bad. So we're going to throw that one out. If x equals the cube root of 100, though, then y is going to equal 100 over 100 cube rooted and squared, 100 over x squared. And if you think about the powers, that's 100 to the 1 divided by 100 to the 2/3. Well, that's 100 to the 1/3, or also cube root of 100. So let's box those up. This for y and that for x. Okay, so we now have our only valid critical point. So this x equals 0 is not a critical point. In fact, our function isn't defined there. If you look at our surface area, if I have x equal to 0, I'd be dividing by 0. Clearly, I can't make a box with 0 length and have it have a volume of 100 centimeters cubed. So that's why we get this weird non-critical point appearing. But we have a perfectly valid one here. What we'd like to do is verify that, in fact, it is a critical point that's a local minimum. So we're going to show that. Let's grab this part, our first derivatives. So our goal now is to classify the critical point that we found, which was xy equals the cube root of 100 and the cube root of 100. We have our first derivatives, and so from there we can find our second derivatives with respect to xy and xx, yy, and xy. What do we have here? We have the x derivative of that would be positive. This is x to the negative 3. And so we'd bring a 3 down front, so we'd have 600. Sorry, that's x to the negative 2. When we differentiate it, it becomes x to the negative 3. Sorry. Get this cleared up yet. And so we'd bring a 2 down front, so we'd have 400. My apologies. 400 over x cubed. And plus nothing. The second derivative with respect to y would be the same thing. Now positive 400y cubed over y cubed. And the mixed partial derivative, let's take the y derivative of this, would simply be 2. At our cube root of 100, cube root of 100, this is going to equal 400 over x cubed. Oh, that's 400 over 100, that's 4. This is going to be exactly the same. That's going to be 4. And this is going to equal 2 because it's the same everywhere. What does that tell us together? Well, it tells us that we can calculate our discriminant value, or our d value, our test value for the second derivative test. Just a reminder, In this case here, our functions s, ssx, syy, sxy all squared. That'll be 4 times 4 minus 2 squared. That will be 12, 16 minus 4. And that is positive. And this second derivative here was equal to 4, which was positive. And again, remember that mnemonic, or that system for classifying these. This is both concavities the same. When my discriminant value here is positive, that means I've got my combination of, or my multiplication, my product of concavities ends up being positive, so they're both the same. And this tells us that in the x direction, we have a concave up. Together, that tells us that the point square root of 100, or cube root of 100, 100 for x and y, is a local minimum for the surface area. And what does that tell us overall? Well, it means that dimensions that we should select, x equal cube root of 100, y equals cube root of 100. Oh yeah, we also had a z in here. We should probably return what that is. Well, that's 100 over xy. If you do the calculations, it shouldn't come as a huge shock that we get the cube root of 100 again, are the dimensions x, y, z, give the minimum surface area. And what shape is this? This is a cube. The nice, perfectly symmetric shape that has the same dimensions in x, y, and z, has the smallest surface area. Given, there's not quite enough room to write this, but I'll say it, given the fixed volume that we had to work with, given the volume had to be 100 cubic centimeters, this cube with cube root of 100 centimeters on each side is going to provide the smallest possible surface area that encloses that volume. So that's a start to finish word problem where we have to define the functions ourselves and then use all the techniques of critical point detection and then critical point analysis with the second derivative test to classify the critical points.